Hello everyone, welcome to Continuum Mechanics. Today we're going to continue a lecture that we started on the Cartesian coordinate system. At the beginning of the lecture, we introduced the ideas of base vectors, which are vectors that indicate the coordinate directions in a Cartesian coordinate system. And these vectors are orthogonal to each other and have certain properties that allow us to very easily identify the components of regular vectors and regular tensors. So let's start with vectors and then we'll build towards tensor components. So let's say we have some vector u. We can define the components of that vector, the scalar components, as being equal to the dot product of the base vectors times the vector itself, where the components are the scalar product of the base vectors and the vector itself, right? So we would do the base vector 1 dot u to give us u1, the base vector 2 dot u to give us the component u2, and the base vector 3 dot u to give us the component 3. Now if we rearrange this, then we find that our vector u is simply equal to the components of u times each of the base vectors. And noting that the I here is a dummy index. So we're actually summing the value of each component, u1 and the base vector 1 plus u2 base vector 2 plus u3 base vector 3 to build our vector u, right? So this is the basis of how we can define the orientation of our vectors in our space, right? Based on these base vectors. Now let's apply this concept to tensors. And let's start with saying that, hey, we have some tensor f that when we do the dot product with respect to a vector u, we get an output vector v, right? Now let's consider v in terms of its components, where the components are vk, is equal to the base vectors k dot product v, and where we can then take this relationship between v and u and plug it in so that we can say that the base vectors k of the dot product of our tensor dot product the vector u is as follows. Now we can also, remembering our relationship here for what u is in terms of its components, pull that into our equation here. And then we can find the base vectors k dot product in brackets the tensor f of the dot product of the components k and the base vectors the components L, we want to introduce a new index here. The components L times the base vectors L. Now, using the knowledge that we have about scalar quantities being commutative, we can actually pull this u out and do our operation as follows. Well, the base vectors k dot product tensor f dot product base vectors L, all of that times this scalar ul. Now with this knowledge, and also with our knowledge concerning what happens when we do the dot product of two base vectors, we can find this relationship in terms of the components, where our vk is equal to f kl, so the terms, the components of f, times our ul here. So we actually have found the tensor f in component form, and we can see that there is a relationship here between our terms. We have this nice relationship here that indicates which rows and which columns result in the row for VK, right? Now, we can rewrite this in matrix form where our V, let's say it's V1, V2, V3. It's one column and 3 rows. Our tensor F, F11, F12, F13, where our indices, the index K here indicates the row, and the index L indicates the column, right? And then finally, we have our vector U, which is U1, U2, and U3. Now, this operation here, again, because we have dummy variables, is going to be a summation operation. So when we actually execute this matrix and find what is the actual component V1, we will exercise that dummy variable L in order to create the equation which describes V1. So row, column, and the first term in U, let's go ahead and do that. So then we will find F11 U1 plus F12 U2 plus F13 U3. So this with that, and the summation is indicated through that dummy variable, through that L dummy variable. And we can repeat this process. F21 U1 plus F22 U2 plus F23 U3. And then we can find the last one here. So each of these, this row times a column, gives us the row term U1. Similarly, this times a column is V2. And then this times a column is V3, right? So we're doing that summation property by identifying the dummy variable. So let's get this last one, F31 U1 plus F32 U2 plus F33 U3. And now we actually have the 3 equations, which are the 3 components of this vector V. And we can say that this is where F, K, L, our components of F, are equal to the base vector index K dot product tensor F dot product base vectors L. And this subsequently implies that then our tensor F is simply equal to F KL, the components of F, times the base vector K and the base vector L. Now let's continue here by seeing, is there another way that we can define this matrix relationship, or this relationship between our terms? And there is. If we remember, when we were working with vectors and tensors in a coordinate-free system, we found that we could do the transpose of a tensor, the transpose of a vector, and find that relationship. So let's do that. Let's say that the output vector transposed, this is a property, is equal to the input vector transposed times the tensor transposed. So this is a property that we found. Now, if we illustrate this in matrix form, when we transpose a vector, we switch the rows and the columns. So now, instead of having one column and 3 rows, we have 3 columns and 1 row. And there we go. V2, V3 is equal to U1, U2, U3. And then we are transposing our F here. So we're going to be switching the rows and the columns. So our I diagonal will remain the same. But these off diagonal terms are going to switch positions. All right, so we're switching these terms with their normal positions. Now, when we perform this operation, we can check to see, hey, does the V1, the V2, and the V3 that we arrive at here remain identical? Even though we've switched our rows and our columns here, they should remain identical. Well, let's complete the operation. Okay, so let's do that. Well, then we're doing this operation with respect to that, and we'll repeat that for each of these terms. So this is, V1 is this times that. So we're doing the summation of these terms, and then we would repeat that for V2 with the second column of the vector F, and then the third column for V3. So let's do that. So U1, F11 plus U2, F12 plus U3, F13. Repeat this for the next one. U1, F21 plus U2, F22 plus U3, F23, and then finally U1, F31 plus U2, F32 plus U3, F33. And if we were to compare this with our previous solution, when we didn't do the transpose, we'll find that they are identical. The only difference is the placement of the U components before the F components in each of these V1, V2, and V3 equations, right? And so we've clearly found this great relationship, and we've done it all from the origin of our base vectors, right? So now let's go ahead and move on to the idea of dyads. So a dyad, or a dyadic tensor, is something that we just generated when we found that our tensor F was equal to F KL, so the components of F with indices KL, times the base vector K times the base vector L. That process of multiplying two vectors with respect to each other is a dyad. So we can say a dyad is say we have a vector A and a vector B with respect to each other, or we have our base vectors, so you say a base vector 1, a base vector 2 with respect to each other, or even if we have something like an I and a J next to each other, we've created this dyad, an I and a J with respect to each other. Now, sometimes the symbols or the way that we indicate dyads is different. There's a couple of notations. So some people just say, hey, a dyad is simply A and B. Some people say a dyad is A with a circle with a cross in it and B. And other people say that a dyad is a vector A and a vector B transposed. Now, what's important about a dyad is that the product of a dyad forms a actual tensor, right? So we build a tensor from this vector product, and that's what indicates a dyad. And the reason that In this last example, they put a transpose, is because when you put it in matrix form, you need to transpose one of those vectors in order to build your tensor, right? Rows times columns, you build it up, and you build a tensor, right? So the good thing is that all three forms have the same definition and meaning, and often people simply just do this operation here. They just show it in this simple form without any additional notation. Now, operationally, a dyad is defined by the following relationship. And we'll see it from this coordinate-free form, and then we'll also see it in a matrix form so we can more easily apply it. But we'll see that a dyad is defined as A, B, dot product some vector V, same thing as A in brackets B, a dot product of that vector, right? So this three vector relationship that persists between these vectors. Now let's step back a second and let's just see the dyad operation in matrix form so that it becomes clear how this operation functions. Say we have a dyad, a vector, and a vector. I like to just remind myself that, hey, this is the same thing as A times B transpose, where we switch the rows and columns, such that we have A1, A2, A3 times B1, B2, and B3. Now from that, we can build our tensor, where we do rows and columns. So row, column is the first term, row, the second column is the next term, row, the third element is the third term, and then we continue to shift downwards and shift over, and we build our little matrix here. So let's try that. So we start with the first position, A1, B1, and then our second term, A1, B2, and our third term, A1, B3. Right, so we've built these three components where our second index, our second term, indicates, column 1, column 2, column 3, right? If we repeat this process, we can then build up this dyad tensor. And then finally A3, B1, A3, B2, A3, B3, right? So now we've got this idea in our head of how to perform a dyad, and also that in order for this operation to work, we've got to do rows versus columns to build up this tensor, right? So then operationally, if we go back to that relationship, AB dot product V is equal to A in brackets B dot V. If we go ahead and try to exercise this in matrix form, remembering this AB that we just found, we can go ahead and put that AB. Let's do that. Let's just copy this. Oh, make it a little bit bigger. Copy. Paste our AB. Right, so that portion. And the dot product of our vector V, so say V1, V2, and V3. And we'll go ahead and say that is equal to the vector A1, A2, and A3 times the scalar products of vector B and vector V. And remember that when we do the scalar product of two vectors, it is the terms II, so it's basically BI, VI is the scalar product. So let's go ahead and fill that product in. So B1, V1 plus B2, V2 plus B3, V3. That is our scalar product. So when we perform these operations, we're able to actually build up our the solution to this actual operation, which is in the end a vector. Now, this operation implies that the multiplication of a dyad is not commutative, such that if we start with our original equation again, if we write it again, let's just copy it, makes it a little bit easier. This operation, and if we wanted to switch our order of the operation, or switch the terms here, the right-hand side of our equation changes. And if we then wanted to do the second equation in matrix form, we could. Let's do that. If we did this second equation in matrix form, so let's copy these terms. We've switched the order here between from the left-hand side of the one that's above it to the order here. Since we switched that order, in order to maintain a reasonable solution, we need to switch and transpose this vector. Okay, so we got the left-hand side of equation 2. And for this to be true, our right-hand side would have to be the following, or be equal to the following. Okay. Well, the right-hand side must be equal to the transpose of that tensor times V1, V2, and V3. So in essence, we're finding that when we switch the order of B and A, we're transposing the product tensor. So when we switch the order from A to B, we switch it to B to A, we're in essence transposing the product tensor of that dyad, right? The dyadic tensor is transposing, right? So it's a very interesting property of these dyads. So then we can find that the transpose of AB in matrix form. Well, let's start with the idea of the transpose, and remember our notations here. The A, B could be this circle with X symbol, or we could think of it as A and a vector T transpose to form the tensor. Well, when we do the opposite, when we switch the order of B and A, we have our B here, circle cross A, we end up with B A transposed, right? Where our B is, 3 rows, 1 column, and our A becomes 1 row and 3 columns. So let's try this B A dyad, okay, in matrix form. Well, then B1, B2, B3, right? We got 1 column, 3 rows. B1 is a row, B2 is a row, B3 is a row, and then we switch our A, so A1, A2, and A3, right? And we end up with our nice little tensor here. And again, our first term is B. We do this to that for the next term. So that's that term. This to this is this term. This to that is that term. So let's build this operation up and find our terms. So B1, A1, B1, A2, B1, A3. All right, that's our first row. Okay, now B2, A1, B2, A2, B2, A3, and then finally B3, A1, B3, A2, and B3, A3. Now, if we were to go and compare this dyad tensor to the previous one we found, we'll see that we've actually transposed the terms. We've literally transposed the solution, the terms of this dyad tensor by simply switching the order of the vectors, right? And remembering that we're going to be transposing one of these terms to actually form a proper tensor here, right? So that's actually pretty cool. So now let's go ahead and do a dyad example, and let's try to work this example to identify some more algebraic relationships with dyads. So let's start with a dyad example. Say we have a dyadic tensor, capital Phi, which is equal to a vector A1, B1 plus vector A2, B2. So these are a sum of dyads. Well, if we have the sum of these are several, I guess we could say subtensors, tensor related to vectors A1, B1, a tensor for A2, B2, a tensor for A3, B3. Excuse me, put that there and put this one here as well. Well, then if we did the transpose of this overall tensor, then we would be transposing each of these subtensors, switching the order here, right? That would make sense, correct? Because we would be transposing each sub-element, a subtensor. So we've kind of found this nice relationship here when we're summing tensors. Now let's remember, we found that if we had some tensor f, it could be defined as the components fk times the base vector k and the base vector l, where we have these two base vectors form a dyad that builds us a tensor, right? Okay, well then, if we then did the transpose of this tensor, we would find that the components f, k, and l remain the same, but we can switch the order, or we switch the position of our base vectors. So we can actually find the transpose of a tensor by switching the order of our base vectors, by transposing, in essence, the base vectors to switch the position of each of these components. So as a consequence, we can say that f transposed in terms of I and j is equal to switching the components or the indices of our components j and I, so such that the transpose can be formed by either reversing the order of our base vectors, so switching the base vectors themselves, or by switching our indices, so switching the order that we actually perform our operation mathematically, right? But it's important to note that we can't do this. We can't do both of these. We have to choose one, either switching our base vectors and allowing our components to remain the same mathematically, or simply switching our indices, so changing the order that we perform our operation, right? Now let's look at a couple of mathematical rules for dyads. Let's first look at the multiplication of a dyad by a vector. Let's see how we might perform that operation. Say we had some vector and we did the dot product with respect to a dyad tensor. We could go ahead and then describe the product of that, as v dot a1 times b1 plus v dot, again, the v vector, the a2 vector, b2, and so on, right? So we actually would distribute that dot product through each of the subtensors, right? Which is a nice little relationship there. Now another relationship is what about multiplication in terms of distributed multiplication? So say we had two vectors, a plus b, multiplied by two additional vectors, c plus d. Well, what we're saying is that we would actually distribute that dyad operation, that actual operation. So we'd go ahead and this term and that term and this term and this term. We'd end up with 4 terms, right? Of course. Say a c plus b c plus a d and plus b d, where each of these terms is a dyad. So we're building the sum of these tensors together. Each of these meaning a tensor. So from that, we'd also say that hey, we had some dyadic tensor built from a and b. Well, if we replaced the vectors a and b with the components of the vector times the base vectors for each of these, so a k component times base vectors k, and bl components times the base vectors l, then we could then rearrange this and find AK BK is a dyad of the base vector K and the base vector L, right? So we can actually build this out, and from this very easily in this component form identify where these components are flowing. And excuse me, one little typo here. This B is an L here. Right? The index on the B is L, not K, right? So we can very easily build up our nice little dyadic tensor from the base vectors and the components. Now some rules about symmetry and asymmetry. We can say a dyad is symmetric if that dyadic tensor is equal to the transpose of itself, right? So in component form, Fij, so F with indexes Ij, is the same thing as Fji. So our off-diagonal terms are identical. And we could say, F12 is equal to F21, F13 is equal to F31, and F23 is equal to F32. Right, so our off-diagonals are identical. We can also find that a dyad is antisymmetric if the tensor F is equal to the negative of the transpose of itself. So in essence, Fij is equal to negative Fji, the components. Now, in order for this antisymmetric form to be true, our diagonals must be equal to 0. In order for this to be true. Because when we do our transpose, nothing happens to the diagonal terms. So for this to be true, we must actually have a 0 diagonal. And we can, going back to our introduction to tensors, we can clearly exercise that this relationship with a general tensor to illustrate that those must be 0. Now, we can also describe our identity tensor in dyadic form, where identity is equal to the Kronecker delta's elements, m and n, times the base vector times the base vectors m. Excuse me, this pen is acting up. Okay, so the identity tensor is equal to the components of the Kronecker delta times the base vector m and the base vector n, which we could then describe as, or we could break down, knowing the terms of our Kronecker delta, as base vector 1, 1, base vector 2, 2, and base vector 3, 3. We can actually build our identity from our base vectors, which is nice, because what if, you know, our Cartesian coordinate system changes, our base vectors change, but we still can maintain that identity in any orientation in our coordinate system, right? Okay. So now let's go ahead and look at the tensor and scalar product. So the product of two tensors is itself a tensor. And the Cartesian components is defined naturally by using the dyadic representation in operations between the base vectors. So by introducing our base vectors, we can very easily determine this operation, the product of two tensors. Now let's start this process. Say we have a tensor F. We want to do the product of it with respect to a tensor G, where our output is some tensor H. Well, let's then define F and G in base vector form, in components, where F, the components of F, Fij, are times this, the base vector EI, the base vectors EI, and the base vectors EJ, right? The dot product of that with respect to G, KL, so we get some new indices here, the base vectors K and the base vectors L, right? Now, since Fij and G, KL are scalars, right? These are components, individual components. We can pull those out commutative. So Fij and G, KL. And then we're left with the operations of these base vectors. So let's go ahead and say I, and let's say EJ dot product EK. So let's take the inner product of EJ and EK and EL. Now let's remember that that when we do the dot product of base vectors, that we end up with our Kronecker delta, right? If we have the product of two base vectors, say this and that, we should end up with our Kronecker delta as that term, as long as our rows and columns are opposite each other. Well, in this case, we have J and K. We can replace that with our Kronecker delta, and then we can rearrange and simplify this, and changing our indices to find F, IK, GKL is the base vector EI and the base vectors EI and the base vectors EL. So we can actually find the product of these two tensors through the base vectors relationship. So then our scalar components of H become simply F, IK, and F, GK. And note that these inner terms here are dummy variables that disappear on the left-hand side of this equation. So, how do we then define this in matrix form? Well, it gets pretty nasty, but let's work through it. So in matrix form, we've got this F, IK, G, KL. Let's put each of these as a matrix. So let's kind of define them. Okay, F11, F12, F13, F21, F22, F23, F31, F32, F33. And let's repeat that for G. G11, G12, G13, G21, G22, G23, G31, G32, and G33. Now we always want to do our rows versus our columns. So row 1, column 1, which indicates our first term in H. So H11 is equal to this operation, and we are summing these terms. So F11, G11 plus F12, G21 plus F13, G31, right? Now if we want to do the next term, term in H, so the term H12, right, where it's on row 1 in column 2, well, we're going to do that with row 1 of F and column 2 of G, right? And let's go ahead and change the color here so it's a little bit easier for us. Right? That and that. So we'll end up with F11, G21 plus F12, G22 plus F13, G32. And we can continue to repeat this process for the other terms of our H tensor, and in the end, there exists 9 equations for the 9 components, the 9 terms in that H tensor, right? That product tensor H. And so, simply by using the base vectors and identifying the proper indices, we can build up the product of these two tensors. So an important thing for us to note is that tensor multiplication is not commutative. We can't just simply switch the order of these tensors and produce the exact same solution. So if we do switch the order, we find the following relationship, where it's the tensor G transpose, the product of that is F transposed is equal to F dot G, right? So it's not commutative. We have to, this is the relationship that is enforced. Now, interestingly, the scalar product between two tensors can be computed in 2 different ways. You can actually compute it in 2 different ways. One of the ways is to use the outer product, where the dot product is the product between the 2 furthest base vectors, so the base vectors on the outside, or farthest from each other. And then there's also the inner product, where we do the dot product between the 2 closest base vectors. So let's start with the outer product. So say we wanted to do the outer product of F and G. We'll denote it by 2 dots that are adjacent to each other. And then we would go ahead and then define brackets. Oh, come on. Okay, in brackets, Fij, base vector I, base vector j, dot product G, KL, base vector K, base vector L. Okay. Now let's go ahead and do this outer product. So we're going to take the outer terms and do the operation. So what are our outer terms here? Our outer terms are I and L, right? So let's pull out the scalar components Fij and JKL, and let's perform these operations. So base vector I, dot product, base vector L, and base vector J, dot product, base vector K. Now when we perform this operation, remembering that if we have rows and columns, that we can replace these base vectors with Kronecker delta, we'll find that the outer product is simply F, LK, and G, KL. Okay? Now let's repeat this process for our inner product. Let's copy, paste. Our inner product was denoted by dots above each other, or above and below each other. Above and below each other here. And let's also correct that on this one. They're to the side of each other, and here they're above and below each other. When we perform that operation, and let's copy this here as well to just make it a little bit quicker. When we perform that operation, we're looking at the two closest base vectors, so we want to perform that operation. And our two closest base vectors we're going to consider as between the two is this one and that one. So if we consider that, then we'll do the base vector of base vectors I, dot product base vectors K, and the base vectors J, dot product the base vectors L. When we find our Kronecker deltas and we regress down our identities, so we eliminate the ones that we don't need, we'll find that F, LK, and G, LK are our terms of this inner product, right? And so by using and manipulating the relationships that we know about dyads, the relationships we know about base vectors, we're able to do a lot of interesting things from identifying vectors, identifying tensors, doing the dot products of tensors, and doing the inner and outer product. Now in our next class, we're going to look at the cross product operation in terms of base vectors, and understand how the solutions of these are in Cartesian and in a Cartesian coordinate system. So that's it for today's class. Thank you for listening to our lecture, and that's it.